Well, welcome to this second lecture, which is very meritorious in a holiday day to have a lecture. So what I wanted to say today, I wanted to explain a little bit, is to go a little bit further on the things that we saw the other day. And so we were talking a little bit about this quantum information science and quantum technologies, what it's all about. And today I will still talk a little bit about that, and then I will show a few things of quantum communications and quantum computing, and I will leave quantum simulators and metrology for the next time. So the most important thing of this quantum information theory is to remember that information is physical. So because everything that we do, it's encode or transmit or decode information, it has to be in a physical support, which means that it follows the laws of physics. And this is what we were saying the other day, that if we do information using quantum physics, the laws of quantum physics are a little bit different, and therefore we can do some things that they are a little bit different from classical information theory, because the physical laws that we are using are a little bit different. So as we were saying the other day, there is 3 steps in any of these protocols that we are going to use, which is prepare a quantum state. And this is this thing of here, I was saying this is how to prepare a quantum state. Okay, so, and this is very important. And here I put a picture. Do you remember that we're saying, for instance, we can have any 2-level system. So we are going to have any system which is of the form system, which this is just notation. It doesn't have any importance. It's like to say this is a vector on the which lives in a Hilbert space. We use this notation, but it doesn't mean anything. It's a comfort. It's a very easy notation that we use. And we were saying that we will use normally always qubits, so 2-level systems. And the reason that we were using these 2-level systems, which is any of these, for instance, ions that it's here, we say that we have these states which we call 0 and 1. Okay. So ground state and excited state of a 2-level atom, or spin down, spin up of a spin of electron. And this is what we call it a qubit. And we use qubit because qubits encode information, transmit information, and decode information much more efficiently than other systems which are higher dimensional, because we have to have access to each of these states, 0 and 1. We have to be able to address them separately. Okay. And so what we have to remember is that qubits means efficiency. Efficiency in manipulating, in coding, transfer, and manipulating. Manipulating everything. So, and we will call it like that. Our 0 will be just a vector, which will be this one. This is what normally it's called the computational basis. And the 1 will be written like another vector orthogonal to that. Okay. And then we had this kind of manipulate. And we were looking the other day and we say, we did already some gates, and we say that when we work with isolated systems, we know that any manipulation that we can do, it has to be an operation which is unitary. Okay. So because quantum mechanics is linear, and this Schrödinger equation gives the evolution to a unitary evolution. So this has to be preserved. They are unitary evolutions. And then we have measurements, and the measurements we are saying, and we will see it, okay, we have, as a result of measuring something, we have probabilistic outputs. Okay, well, this probability of getting the output M, normally we will call it that this is, if I have something to measure, so that will be a measuring operator. And this is very important because quantum mechanics is a probabilistic theory. And we put it like that. Okay. So, and then we say something that today I wanted to go behind and to say it again, that the most important thing is that in quantum physics, we have more resources, which we don't have it in classical physics. And these resources are basically 2. One, it's the fact that we can have quantum superpositions, and the other, it's the one that we have quantum entanglement. And since these resources doesn't exist in classical physics, we have the capability of doing things that we are not able to do with classical physics. And this is the surprises and the interesting part of these quantum technologies. What can we do that we cannot do classically? And this is what I would like to talk today. So let me refrain again what was these quantum superpositions, okay? So you take any of these single qubits, so I have here several qubits. And when you want to do a quantum superposition, the other day we were putting a Mach-Zehnder interferometer, which is normally with light. So we were doing something like that. So we will look at again. So we have here a beam splitter that splits this. I have a mirror, another beam splitter here, and a mirror. And then I look at the outputs. I put something to look here and something to look here. And I look at the outputs when I send light from here. Okay, but this is normally done also with atoms. So what is this Mach-Zehnder interferometer? And we were saying Mach-Zehnder is very important because what a beam splitter does, okay, remember if that was something that was entering in X, we were saying, well, a beam splitter, what it does is splits. So half of the photon goes in this direction and half of the photon gets reflected in the other direction. So that gives something like with a phase here. It's not very relevant.
Anna, the photon goes in both directions at the same time, no?
Sorry, the photon goes in both directions, exactly. It's the same photon. Both, okay. It's a split, a single photon. You can do it with a single photon. Normally when we think
but it's in two places at the same time, no?
Yes.
Okay. Yeah.
So how do you do it with an atom? How is the equivalent of doing that with an atom? Well, with an atom, you do the same. So you have these atoms.
How can you rotate this? You rotate the polarization of photon.
You have the polarization of photons, so you take a two level. If you
rotate by using this, yes. This is like a rotation.
Let's go slowly. Okay, so you can do that with classical light. Okay, that's not a problem. And you split your beam of light in the X and in the Y direction. So I call it this is X and this is Y, and this is what it's a beam splitter. That's not a problem. But you can do that at the single photon level. Okay, and now you quantize, and this is polarization in this case. Okay. So I have a photon which is polarized vertical. I have a beam splitter which is a 40 degrees polarization plate. Okay, and allows the photon to transmit. Okay, and to reflect. Okay. So if you do it with the polarization of a single photon, okay, or if you do it with the polarization of light. So you send light, not a single photon source, through a beam splitter, 45 degrees polarization beam, and you know that with half of the light will be transmitted, and the other half will be reflected. Now you want to do that really at the quantum level. Okay. So how do you do it with an atom? So you have an atom, and this is a block sphere representation, but it doesn't matter too much. So the equivalent of a Mach-Zehnder interferometer for light, it's what it's called a Ramsey interferometer for matter. And it's exactly the same, okay? So I have my atom, which is a two-level system. I will put it here. So my state preparation, I have my two-level system, and I imagine that I have everything which is originally in my ground state. And now I sent a pulse, which means I sent light, which is resonance between this level and this level. So this is H omega. Okay, this is the light that I sent for a period of time, 3.5, in such a way that I do a superposition. So my state after that, it's a linear superposition of my atom, or the electron, which is in my atom, the electron that I am addressing, which is in the ground state and the first excited state at the same time. Okay, and now I let this system to evolve, okay, for a time which is called pi. Okay, so this is free evolution. So what happens is that my initial state, okay, so which was A, so in the ground state with momentum P, okay, now I have split it, and I have also excited state, which here it's called B, which has momentum P plus HK. Now I let them evolve. Okay, so this is the equivalent of the phase. So in this picture, so I go from having the ground state, I go to in the block here to this equatorial plane. I let it evolve, so it acquires a phase. And now I have to do exactly the job of the second beam splitter, which is this one of here. So I have to put again a p½ poles in order to recombine these two paths. And then I measure. Okay, so it's exactly the same thing for atoms, which is called Ramsey interferometer or Ramsey-Boldet, the Namax-Sender interferometer. So, and when we do that leg, it happens exactly the same. So my state, and now this is the ground state of my interferometer, okay? After the first 5 poles, it goes to 1 square root of 2, a combination of ground state plus excited state, okay? And now I let it evolve, and after I let it evolve, this goes like 1 square 2 ground state plus in the excited states acquires a phase. And now I recombine it again. And when I recombine it again, I have that this is my state 0 is 0 plus 1 plus e to the I phi 0 minus 1. And I do a little bit of algebra, which is very simple. And I have that this is cosinus of phi 0 minus sinus of phi 1. So I have the interferences.
Anna, so what is the unitary matrix that represents the beam splitter in this case?
The unitary is always the same. So it's this Hadamard. Okay, so it's this 1, 1, 1 minus 1. Okay, so this is the unitary way.
No, but in this case, it acquires a phase, no?
Sorry?
It acquires a phase, no?
The phase is just the free evolution. So the phase is exactly like we were doing, is a unitary evolution, which is this one. This is the superposition, the first p½ poles, the unitary, and the pi is 1, 0, 0, a to the I5.
Okay. Yeah.
So this is exactly, and this is what I wanted to tell you, no? So, and then you look, depending on the free evolution, until you apply your second p½ poles here, so you shine the laser in your 2 atoms, you will find that the result that you get, that the electron is in the ground state, okay, will be oscillating, and obviously the probability to find it in the excited state will be exactly the opposite in phase. And this is exactly the what we call it, the interference, superposition, the double slit, the Young experiment. All these things are exactly the same. Okay, so.
Yeah. Why do you choose this unitary? This is, I think, is Hamadad gate. Why? What is the importance of choosing this more than other unitary matrix?
Why is it important? Well, first of all, because evolutions in isolated systems has to be unitary, that it's unitary, and then we will see it, which is the importance of that. So let me write it like I was writing it the other day. I will do this in the same way. No, I will say I have my initial state, which is, for instance, in the ground state. So I have my 2-level atoms. So this is my 2-level atom. Now I apply this gate, which I call it Hadamard, which is this unitary. I apply a phase gate, and I apply another Hadamard gate. Okay, and I look what I get here. And this, you can do it by hand. So I told you that the Hadamard is this unitary, but already we don't need to even, it's very intuitive. Okay, so we don't need to do the maths. And the phase gate, it's putting a phase. But as again, I'm trying to say, it's not necessary to do the maths, because obviously we can find this result when we multiply these matrices, H, P phi, H. But it's very easy, because what it's telling us, this Hadamard gate, which is fundamental for everything that we are going to do, is create a superposition, make a phase, and recombine these paths. And this is the basic of quantum computation, okay? And I will explain you why. So why this is so important. So this very simple circuit, we will keep it like the fundamental, I will say almost the fundamental gate or fundamental state of of fundamental circuit of quantum information. And we will see why this gives a lot of advantages. Okay. And now let me go to the second thing. So I say quantum superpositions are very important, and quantum entanglement, it's the other resource that we have. So, and by quantum entanglement, we always will understand that it happens when I have two or more systems that interact. And we have to do the same now, and we have to understand what happens here. So I have of course, I can have many systems that are different. This is not related to qubits, it's related to the structure of quantum mechanics. Okay, so I have a system which normally, and now I will start always to call it Alice, okay? And I have another qubit, which is in possession of Bob. I will call my system A and B. And of course, Alice has this phase, so it's a two-level system or spin. And the same happens for Bob. And now these guys, they interact between them, okay? So they are interacting. I make them to interact. And then I can say, well, this first qubit lives in this Hilbert space, the second qubit lives in this Hilbert space. Quantum mechanics tells me that I have to write it like that. And now I have a basis of this system. I have my basis, which is, for instance, this one. I can have other bases, but in the computational will be 0A times 0 for B, for Bob. I can have 0 Alice times 1 Bob, 1 Alice, 0 Bob, and 1 1. And I told you the other day that this is too long to write it. So we will write always these bases like that. 0 0, 0 1, 1 0, and 1 1. Okay. So any state which lives now, state that it's in the space of Alice and Bob, a priori, if this is a basis, I will be able to write it like a linear combination of the elements of the basis. So that will be like that.
So Anna, let me ask you a naive question. So let's say A and B are identical.
Yes.
Not all these bases will be allowed, right? You need to have the right permutation symmetry. Does that happen here or no?
Well, let's say I'm going to assume here that I know which is Alice and Bob because they can be identical,
okay.
but they're going to be separated physically.
Okay, yeah, okay, that makes sense.
So it will be more complicated if I talk about fermions, okay? But imagine that I don't care at this moment. So they are physically separated.
Okay, that's fine, thank you.
So when you have it like that, you don't have any problem. Like here, I and J, so I obviously can be 0 or 1, and J can be 0, 1. So this is just standard algebra of mathematics of quantum mechanics is a linear combination. So we will say that a system like that, I will say that any system that belongs to the system Alice and Bob is not entangled. It's not entangled. If and only if I can write my state psi AB like a system in Alice times a system in Bob. Okay, and let me explain you what it's that. Well, this guy belongs to the Hilbert space of Alice, and this guy belongs to the space of Bob. Okay, if this state it's like that, we call it that this is a product state because it's a product, or it's not entangled, or it's separable. Okay, so in any of these guys like that, so if I have a state which is like that, and I will show you, which is of this form, for instance, then whatever I measure in my state, so if I look, which is the expectation value of an observable, whoever this observable is in my combined state, well, there is no correlation. So this will be measure this observable in Alice and measure this observable in Bob. Will be exactly the same, okay? So in some way, it's like I have Alice, and if they are not entangled, I have Bob, and they don't talk each other. Although these guys, since I have 2 qubits, different Hilbert space of dimension 4. So for instance, the state like that, Alice has an atom which is in the ground state, and Bob has an atom which is in the ground state. Well, this is not entangled, absolutely not entangled. Okay? But if the system is entangled, if this system is entangled, I will say it is entangled. It's a negative definition. If I cannot write it like that, like a system in Alice times a system in Bob. So it will be like if we had something like that. Now this is Alice, and this is Bob, okay? And in some way, they have correlations between them. So if this is entangled, what it will happen is that there are observables, maybe not all, but they are observables, which they will not be. And these are the correlations, quantum correlations, like measuring my observable in the system of Alice and measuring my observable in the system of Bob. It simply is not like that, okay? So if that happens, I can say, okay, if my state it's, and this is very important, if my state is entangled, so I cannot write it like that, there is no possibility that I write it like that. That means that this state, there are many ways we can do it. So it's entangled. It means that it violates Abel inequality. It means that it cannot be prepared locally. There is no way that if there is an oracle who says, Alice, you prepare your state like that, and Bob, you prepare your state like that, you will have this thing. That will not happen, okay? So with all these things, we have to, and we will see that indeed, this is a very strong resource also for quantum information. It's a resource that it doesn't have, a second that I have to plug my computer. It's a resource that it doesn't have any analogy in the classical world. And now you can say, well, how do you prepare that? Because it has to be a unitary operation, because we say that this is something that we can do. And this is what we wanted, we were saying the other day, and now we will see the consequences of that, okay? So how do we do it how do you create this entanglement? So you have your system A and your system B, and you want to create entanglement. So we have to see how are the unitaries. And this, of course, you have to have 2 qubits. This is the simplest case. You can have more, that it doesn't matter, but this is like that. So I have my qubit, that imagine that I put my qubit in 0. Okay. I have a second qubit. So this is my 2-level system and this level system. I also, initially I put it in 0. Now in the first guy, I do my unitary, which is a Hadamard. I prepare a superposition. And in the second guy, okay, now nothing happens here. And now I do what it's called a C0 operation. Okay, and now I look what happens. So this C0 operation, it's a C0 gate. This is what it's called, very important. Maybe let me write it properly. This is a gate which makes interactions between the first qubit, this is Alice, and this is Bob. Okay, and the gates, you can write it in many ways. You can do what it's a truth table. And this is the equivalent of the classical NOT gate, okay? So control gate. And now you have it like that. So you can write, for instance, the truth table, and you want to see how it is. And then I will write the unitary. So this is like that. So this is a truth table like that. So you have the control and the target qubit. And now the control, which is Alice. So this is Alice and this is Bob. Never changes. So you have 0, 0. And as a result of that, you get 0, 0. You have 0, 1. And if the control is 0, you don't change anything on the target. 0, 1. Now you have 1, 0. And now you have to change because your control is 1. So the control is equal, but the target is 1, has to change. And 1, 1 is the same. So the control is the same. And the target has to change, 1, 0. So you can write that in many different ways. Okay, but it's relatively, so let me write it as a unitary. So if I wanted to write it as a unitary, this C0 gate, and it's very easy to check that it's really a unitary, it makes something like that. Okay, so here you put 0, 0, 0, 1, 1, 0, 1, 1. So it doesn't do anything when the first byte is 1, but it flips when the first one is 0, but it flips when it's 1. So it will be like that. This is a C0 gate. All the other things are 0, 0, 0, 0. And it's very easy to check that C0 times C0 gate, it's 1. So it's a unitary. So it can be done physically. It's a unitary, okay? So we have done it with the truth table, but now let's do it like that. Okay, so let's reproduce that in this way. So I put it like that with the quantum circuit, which is very easy to and realize that in order to create entanglement first, I have to create superpositions. Okay. And now I do this right here, and now I write it slowly because we are going to use it. Okay. And this is, okay, so if I start by my state, which is 0, 0, and we don't need to do anything, so what happens? Let's put it with an example. So I start by 0 of Alice and 0 of Bob. Alice goes to Hadamard. So it goes to 1 square root of 2 of 0 plus 1. And Bob, nothing happens to Bob. So now I have 1 square root of 2 of 0, 0 plus 1, 0. Okay, so this is here. We are after the Hadamard. And now we put the C0. But we saw the C0 that if the first bit doesn't change, so this is 1 square root of 2. So if the control is 0, I do nothing. And if the control is 1, I change the target. So since this is 1, 1, 1. Okay, so this is an entangled state. There is no way that I can find, it's impossible to write this state, which now I will write it like that. Because this is, sometimes people call it a singlet, which is exactly the same, it's a singlet, okay, of 0, 0 plus 1, 1. This cannot be written, you can try as much as you want.
Is any way of doing the inverse map, inverse operation, if you given entangled state to go back to fundamental state?
That's a good question. Anna, what do you think?
Say it again because I didn't understand. Say it again.
Anyone practically of doing the invertible operation, given a tangled state, then go back to fundamental state, to basic state.
To get and Jade set the state. I'm not sure.
I'm
not hearing you very well. Sorry. I mean, maybe Omololu, you are hearing better. But
yeah. So you're saying, can you map back from the entangled state to the state before entanglement? Is there an inverse operation?
Yes. This is a sequence of unitary operations. This is a super good question. Of course, you are completely right. So if this is a sequence of unitary operations, I can do, and then I will show you, because this is a super good question, we can do this set of operations backwards. Okay, so I start from here, and now I cannot write, I can write that up.
Hello, Anna, I couldn't hear you. I don't know if it's me. Hello, Anna, I cannot hear you. Can everybody still hear Anna? Because I cannot.
She's muted.
No, we can't.
Can you unmute Anna?
Okay, so I think she's back. Anna, could you unmute? Yeah.
Yes, I hear now, and let me see. Whoops.
Yeah.
Yes, I don't know what
Could you
happened.
share your
But
screen? Yeah. Please share your screen again. Yeah.
So indeed, this is a super good question. So yes, any unitary operation is unitary. So how do I go back? I go back doing the UDAGAs, okay? So absolutely, and we will use it to do teleportation. Well, yes, we will use it to do teleportation, okay? So now let me finish with this quantum entanglement here. So these guys, of course, there is, let's put it like that, okay? Let me write it like that. So I will write it in general. So this is psi plus minus, and then another one, which is 5 plus minus, which will be 0, 1, plus minus 1, 0. Okay, this is a basis of, so this is entangled. This cannot be written like something on Alice times something on Bob. It's impossible. Okay? So, and it's also a basis. Okay, so I told you before that there is a basis. So I have a basis for these 2 qubits, which is 0, 0. This is a product basis. 0, 1, 1, 0, 1, 1. And this also answers your question. And now I have another basis. So this is a basis of product states. Okay, of product states, not entangled. And now I have another basis, which is called the Bell basis, which is this one, P plus, psi minus, P plus, P minus. And this is the Bell basis. And they are maximally entangled. And now it also is, you do it with a unitary. So therefore, there is a unitary, more or less complicated, but in this case, we know which goes from one basis to another. So you can go from a basis which is completely entangled to a basis which is non-entangled. And this is very interesting because it means that I can write a state which is separable, so that it doesn't have entanglement, as a linear combination of these elements of this basis, which are entangled. And that doesn't mean anything, okay? So one has to be careful in this sense. So I think some kind of things why this thing is so important. Okay, so these things are important because of the following. So again, because I would, even if this is the only thing that you remember at the end, this is important. So, and I like to insist, there is no information without physical implementation. Doesn't exist. Okay, so whatever you have, information is physical. Information is physical and therefore follows the laws of physics. Okay? And now I have said that having this this kind of superpositions and entanglement gives some surprises. Okay, and this is the list of surprises that I want to show you a little bit fast, maybe not all of them. First of all, cloning. Cloning classical physics is possible. You take your photocopy paper and you clone it. Okay, you have identical. Cloning quantum systems is impossible. And this is, the reason is because superposition of linearity. Randomness. randomness is something that it doesn't exist classically, okay? Everything can look which is very random, but at the end, the randomness of a contribution, it's the lack of knowledge classically, even if it looks, but if we could know everything of a system, we will not find this randomness. But quantum mechanics is random by default, this we know. So entanglement allows us to share randomness, and this is also very important, okay? Quantum teleportation, obviously we cannot teleport classically, but quantum, we can teleport. Not teleport a particle, but teleport the state of a particle. And quantum algorithms they are important because they use superposition and entanglement, and they allow to solve problems that we cannot solve with otherwise. Okay, this is why this is very important. Cryptography, well, entanglement and non-locality, which is another source, but entanglement mostly allows to communicate privately, and we are sure that nobody has ever seen this message, or if somebody has seen it, we know it. Okay, of course you can say, well, is that important? Well, this is very important because many of the things, even ourselves, I mean, you don't want that anybody knows which is your credit card or your code in your telephone, so to pay with that and so on. So you need to have security, okay? Metrology, can you measure something? Can you imagine that you can measure, for instance, with several, even 3 seconds of advance, if it's going to be a tsunami, for instance, in the ocean? So for Japanese, 3 seconds of difference means the difference between having a big problem in the country or not, because they are prepared in the place where they live to stop all the nuclear centrals, all the transportation in 3 seconds. They have prepared that. So can you measure that? Okay, so quantum metrology, which allows to do its things using entanglement. For instance, let's say it's a very silly example, but it gives an idea. Imagine that you want to measure the population hair of the world, of the whole world, right? So you have to measure all the hair of the world, of all the people. So quantum metrology tells you that you can do that with being wrong by a single hair of a person, right? So this is 10 to the 18, okay? And you can miss 1. So you can do it with this precision, or you can measure time in such a way with the atomic clocks, in such a way that I think you will get, an atomic clock will get approximately, I don't want to say, but it's of this order, 1 second delay on the time of the universe. Okay, this is the precision that can do. Quantum communication, you can do things that you cannot do normally. Okay, so let me see some of them. So quantum cloning. Okay, so probably we have seen this quantum cloning, and I want to put this gate that we have done. So let's go like with the typical circuit. I like to do it in circuits because it's very nice and you can reproduce everything after. It's very simple. Okay, so I will put this X, which will be 0, 1. So I have, and now I'm going to do the following. Imagine, let me just check what is, without putting a Hadamard, what is this gate doing? Okay, so, and I assume that X is, of course, or either 0 or 1 in Alice. Okay, so this is Alice, like always. This is Bob. I don't put the subindex because here it's very nice. And I have said that, so this is a C0, and the C0 makes, okay, if X is equal to 0, I say that nothing happens, no? Because this is 0, and what it happens is that I put 0. So let me write it properly. The effect of the C0, okay, so if I have X 0, and now I write the C0, I will have X, which means 0, 0, okay? And if I have X equal to 0 and I put 1, okay, I will have here again X, because if X is equal to 1, okay, because I say that if X is equal to 1, okay, I have 1, 1, and I'm saying that right, sorry, and this is 0, so this will be, okay, 1, 1. This is the C0. So when you look something like that, it looks like if my state, initial state of Alice is in 0, what is the C naught doing? It's cloning, okay? Because if I started with a 0, it gives me 0, 0. If I started with a 1, the second copy, Bob, will have a 1. So one can say, can I have really a cloner? And what is a cloner? A cloner means that if I have a state in Alice, whatever, so this is in Alice, and I put here my 0 in Bob, will I have here a cloner so that Bob will clone the state that I have? Okay, so this is Bob, this is Alice and Bob. This will be a cloner. So there is a cloner. It looks like there is if we do that. But then we will see that this is impossible, okay? And it's impossible because assume that I put a superposition. So Alice has the initial state, it's alpha times 0 plus beta times 1, okay? And now I want to do this. Let me write it like that. Alice Bob will be just alpha 0, 0 plus beta 1, 0. And now I do the C naught. Okay, and the C naught tells me the first one stays the same, and the 0, 1 gives me B1, 1. Okay, because the control is a 1, so it changes. Well, it's very easy, trivial to see that alpha 0, 0 plus beta 1, 1, it's not 2 times alpha 0 plus beta 1 times alpha 0 plus beta 1. Never it will be, okay? So we cannot clone in quantum mechanics, and we cannot clone because you can say it whatever, because the mechanics in quantum mechanics, the evolution is unitary, or because it's linear, okay? It's the same, you can show it in the 2 ways. There is no possibility, so here you can see it by linearity, but you can say there is not exist a unitary transformation, which it's impossible, which makes that goes to psi psi. Okay, for any psi. Okay, that will be a cloner, like in a classical cloner. I mean, it doesn't matter which paper I put in the photocopy. If I change the paper, I will have a photocopy of the other paper. Okay, so that has to happen for all. So cloning is not possible. Okay, and this is important in quantum information. It's quite important. Okay, I will leave it here because I don't think it's so important. But remember, cloning, it's impossible. And this is very different from classical physics. Okay, randomness. Now, let me go to these Bell states that we are saying. Imagine that I have Alice, which is here, Alice. And now I have Bob. And imagine that they are far away and they are sharing these entangled states. They have several entangled states. Okay, I will put it like that. Boom, 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 boom. Okay, and these states are all equal, and let's say they share a singlet. And so that means that 0 of Alice, 0 Bob, plus 1 of Alice, 1 of Bob. And they are very far away. Now imagine that you have Alice is here in Kigali, and Bob is in any other city of Rwanda, and they are far away. And now I am Alice, I am here in Kigali, I am in my lab, and now I decided to make a measurement, okay? I measure, and what I'm going to have, well, when I measure, I will do a projective measure, that doesn't matter. I'm going to have that either, and this is very ugly, these collapses that Professor Okunjayi was talking about. Either I will get a 0, so Alice will measure, and it will get either a 0, state 0, or a 1. And obviously, she knows that if she gets 0, Bob, when he measures in the same basis, will get 0 because the wave function has collapsed to 0, 0. And if she got 1, we will have 1 because the wave function has collapsed to 1, 1. And now one can say, well, information is physical. So can I transmit information superluminal, faster than light? than light. So information cannot travel faster than light. It's absolutely impossible. So although that happens, why I'm not transmitting information? I'm not transmitting information because before I measure, I have no idea if I have a 0 or 1. I cannot transmit any byte because I don't know what I'm going to have. This is completely random. When I measure my second qubit, I will have randomly 0, 1. So there is absolutely impossible I can transmit any information in this way. Although quantum mechanics tells me that when I do a measurement, I know which is the result that the other person will have the measurement, but I have to do the measurement. If I don't do it, that it's impossible that I can say anything. It's that useful. This is super useful because although we cannot transmit superluminal, which is, it will be very surprising if that can happen, what that means is that we can share randomness. Okay, so when Alice measured on this collection of entangled qubits, she will have a classical, this is classical because it's the result, it's a classical thing. So she will have a series of 0, 1 on the first, 1 maybe in the third, 0, 0, maybe 1, okay, completely random. And Bob will get exactly the same kind of random bits, exactly the same, okay? They don't need to communicate. They know that when they measure, they are going to have, if nobody has looked at that, exactly the same share of random bits. So randomness can be shared quantum mechanically, but it cannot be shared, among other things, classically because it doesn't exist. Okay, and let me finish maybe with that, which is something that it's nice and we have always look at that, which is, we will see that this randomness is fundamental for quantum cryptography. Quantum cryptography and quantum communications is based on that, okay? So imagine now that we have the following, that we have Alice, and this is the typical scenario, we have Alice and Bob, which are very far away. And Alice, let's put here, she has a state, okay, that she doesn't know. She doesn't have this state, which will be a qubit. She has no idea what this qubit is, and she cannot measure. Assume that she cannot measure. She is a theoretician, has that in the hands. And then she has also sharing maximally entangled state with Bob. So this will be qubit 1, this will be qubit 2, and this will be qubit 3. And her task is send the state of 1 to Bob, okay? So she has access to a telephone, but she cannot send this qubit in any way. Can she do it? Can she teleport this thing? Well, it's easy to see that this is possible and one has to understand it, and it's very surprising because this is something that it cannot happen. So, and this is just a very simple algebra. So this state, it's maximally entangled state, it's singlet. So I will write it like 1 square root of 2 of 0, 0 plus 1, 1. Okay, and now if I want to write which is the total state of 1, 2, 3, 1, 2, 3. So I will say, well, imagine that I don't know how is 1, so it will be alpha times 0, and I don't know alpha and beta. This is what I would like to transmit to Bob times 1 square root of 2 of 0, 0, these are 2 and 3, plus 1, 1 of 2 and 3. Okay, and this, it's like that. It doesn't have too much. So let me write it, and this is 1 square root of 2. Okay, alpha 0, 0, 0. So I do this by this 1 plus alpha 0, 1, 1. The first one by the second plus beta 1, 0, 0 plus beta 1, 1, 1. Okay, so this is my state of 3 qubits. Okay, and now, funny enough, let me just copy that. So this is my state of 1, oops, okay. I have this state. Okay. Maybe probably, but no. Let me write it here because so I have my state, which is this one. Let's say of 1, 2, 3. It's simply this state, very simple state, which is 1 square root of 2 of alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Okay, and this algebraically, I'm not going to do it, but it's trivial. I mean, I can write it in the following way. 1 square root of 2, and this is how I'm going to write it. 0, 0, 1, 2, which is Alice, plus 1, 1 in Alice, with alpha 0, which is Bob, plus beta 1, plus 1 square root of 2, and I go a little bit fast, 0, 0, minus 1, 1, times alpha 0 minus beta 1, plus 1 square root of 2, 0, 1 plus 1, 0, in Alice, alpha 1 plus beta 0, plus 1 square root of 2. This is just algebraic, okay? Minus 1, 0, alpha 1 minus beta 0. So this is the part of Bob. This is Bob. And this is Alice. I can write the state like that. It's very easy to show. Okay? So what that is telling us, that is telling us, I'm Alice and I measure, I have to do a Bell measurement. This is very related to what you asked me before. I have to do a Bell measurement. If my Bell measurement, I'm Alice, gives me that, I'm Alice, I get this state, I take the telephone, I say to Bob, Bob, you have already the state that I had. You have exactly psi. Bob has already psi. Okay, so his state has changed to psi. If I'm Alice and measure that, I have to say to Bob, "Oi, this is not exactly the same," but I have to call him and say, "Listen, you have to do a Z operation, okay, which is just multiply by this unitary your qubit. If I measure this state, I have to do an X operation, and if I measure this one, an X and Z operation." So what doesn't mean? Let me try to put this in another kind of thing, okay? And this is exactly what you asked me before, okay? Can I go the other way around? How do I do a Bell measurement? Well, I have to do the other way around. So now I have 1, it's like that. And now I have, first I do a C naught, okay? And then I do a Hadamard. This is Alice, which has the state 1, the state 2, which is a state which is a Bell state and shared with Bob. So this is Bob, it's a space. So these two guys, they are correlated. Okay, and then I measure here. I measure and I measure. Okay. And what happens when I measure? Well, if I get 0, 0, I'm doing the opposite of before. Okay, when I run my circuit in this direction, when time goes in this direction, and I do a Hadamard and I do C naught, I entangle. When I run in the opposite direction, so I'm doing, okay, I'm inverting the Hadamard. Okay, so I do first a C naught, now I'm doing in this direction. I do a C naught and then a Hadamard and I measure, okay? I do a Bell measurement, okay? So if I get 0, 0, what I know? Well, I know that Bob has already my state, the state that I had. If I get 0, 1, 0, I have to pick up the telephone and say, apply X to your state, and you will have you will have the initial state. If I have 0, 1, I have to apply Z. No, sorry, this is Z. It doesn't matter. A unitary operation. And if I get 1, 1, I'm Alice, and I pick up the telephone. I say, listen, to your qubit, whatever you have, you apply Z to your qubit. And you will get the state that I had before. This is my state of Alice. Well, this is kind of magic, okay? Because we cannot do it classically, because we need entanglement. So we are not teleporting the state physically. So if this is an atom, I'm not sending the atom. I'm just sending the state of the atom. I'm teleporting the state of the atom without knowing which state it was between two locations which are as far as you want, as if this Bob and Alice, they share, and this is the thing which is important, if Bob and Alice, they share an entangled state. So this is the entangled state that they are sharing. Okay. This is what entanglement allows us to do. If I have this resource, I'm able to give this state, the state, and pass it to Bob. Not the physical state, but the information encoded on this state. And it goes here, okay? Just using a classical. Right.
Yeah, Anna, I have a question.
Yes, yes.
So if I have electrons, Alice has an electron, Bob has an electron, how do you know that I only teleported the information and I didn't physically transport the electrons?
No, I don't transport any electron. This is impossible because the only thing that I'm saying that I am Alice and I have 2 electrons, okay? One,
yeah,
I have
I understand.
So, no, then say again.
Yeah, I understand. But what I mean is, I get exactly the states that say Alice has.
Yes.
So Bob, I get exactly the same state. So how do you know it wasn't that the electron really moved?
How I know? Because I have the electrons in my physical lab. I am Alice, and my electrons are in my physical lab. All right. So no electron has escaped. I have these 2 electrons, so I have 2 atoms of hydrogen, and these 2 atoms are there. Okay. So there is not possibility. So it's really, and this will be impossible. Okay. This is impossible. The laws of physics, quantum or classical, doesn't allow to teleport the physical state, but allow to teleport the properties of the state. This is what we are doing.
Okay. Yeah.
I mean, and this is different. This is different. So cloning, it's possible, we know. So there's this Dolly, well, that we can do it cloning, but cannot do it quantum mechanically. But quantum mechanically, we can teleport a state without teleporting the physical state, only the properties of the state. Okay, so I want to prepare, I want to communicate with somebody who is, I don't know, in Mars, and there is no way that I can send physically a state to this person because maybe I don't know where it is, okay, physically, although I can have a telephone or a classical communication that I can contact, I can pass which is the state that this person needs, even if I don't know where this person is, okay, so this is quantum teleportation.
Assume Alice send a quantum state to a qubit to Bob. Then assume that there is the F between them who will overlap or who will disrupt the communication.
No, but this is, okay, but this is a completely different problem. You say, imagine that I will tell you why this is relevant, not today, because, oops, imagine that I send this state to, I have a state which I want to send, okay?
Yes.
Yeah, fine. I mean, I need a channel. That's exactly, you and I, we are sending us a lot of bits of information through our classical channels, which is this computer, okay? And this is absolutely fine. So I'm codifying my voice in an electrical signal, which it's codified in some electrons, and then it's with photons, it's sent it and so on, and then collected. So this is fine. This is classical, and quantum, we do it, okay? But the problem is, can we, so the problem is it's different, okay? So this is one of, if you want, this is a kind of a game, okay? To say, what is this? And we will see why it's so important, this entanglement. Entanglement has nothing to do with any classical resource and allows to do things that we cannot do it, okay? So we will see that this is the fundamental thing of doing algorithms, will be quantum algorithms. And I will explain next time why this is so important, okay? Why we can do things that we cannot do classically. And this because we have these resources and because information is physical. So this is the thing to remember. Okay, so.
Yeah. So thank you very much, Anna. Yeah, there's a question in the chat from Sonia.
Yeah, did measurements? No, the measurements that I do here, no, they don't perturb. No, I have, if I do the measurements perfect, so this is what I'm saying. How do I have to do? I have to measure, Alice in the teleportation has to measure in the Bell basis, has to know if he has one of the Bell bases in her 2 qubits. And this is difficult, okay? In the sense that in the experimental, it's difficult, but this is done because this is just, instead of applying a Hadamard and a CNOT, now I have to apply a CNOT and a Hadamard, okay? And then measure. And then I will have no problems. If the measurements are not perfect, if I have errors, of course, that will change. But this is another part of quantum. So you have to add errors and so on. But now I'm talking about completely perfect things, isolated, so it doesn't affect, no.
Okay, thank you very much. We can take 2 more questions. We're over time, but we can take 2 more questions. Does anybody have a question?
I don't see the questions.
If you have a question, you can unmute yourself and just ask.
Yeah, exactly.
Okay.
Okay, so.
Yeah, so if there are no questions, then let's thank Anna. So thank you very much, Anna.
Okay.
So Anna, please, will you send us the slides, the ones
Yes.
that have the writings, not the blank ones? Okay.
No, these ones I will send you the the right ones.
Okay.
Yes.
Yeah.
Okay.
Thank you very much, Anna. I'll send the recordings also. Thank you, everybody. Yeah.
Thanks.
So we'll meet
Bye.
again next week at the same time. Yep. Thank you. Yep.
Bye.
Bye.
Bye.